Greetings, my name is AimeeMarie and I'm a computer science student from Cohort 3. Today, I will be taking you through application of probability and statistics in medicine. Our case study is about a therapy for breast cancer that was developed by University of Global Health Equities class of 2025. It is said that this treatment has efficacy of 10%, which means that 10% of people undergoing this treatment are likely to recover completely from breast cancer. Our role now will be using a probability and statistics concepts to help a member of a UGHE class of 2025 make predictions regarding this new treatment for breast cancer. To be able to do this, we should be familiar with some concepts. One of them is probability. Probability can be defined as the likelihood of an event to occur, and it is usually calculated as the total number of favorable outcomes divided by the number of possible outcomes. Two other things you should know about probability is that it is always between 0 and 1, where 0 means that an event will always occur, while 1 means that an event will sorry, that 0 means that an event will never occur, while a 1 means that an event will always occur. The second thing is that probability of all outcomes must always add up to 1. Next, there's binomial distribution, which refers to the probability of a success or failure outcome in an experiment that was repeated multiple times. By prefix itself highlights that binomial distribution has only two possible outcomes, either success or failure, which you can also describe as win and lose. There are four conditions an experiment must satisfy before it is regarded to as a binomial experiment. One is that the number of trials n must be fixed. This means that an experiment must be conducted for a finite or precise number of times. The second one is that there are only two possible outcomes for each trial, either success or failure. Third, the probability of success must be constant for each trial, and each trial must be independent, which means that occurrence of one trial must not affect the occurrence of another trial. Now, we are going to talk about the binomial formula, and it is noted as n choose r p to the power of k times 1 minus p to the power of n minus k, where p is the probability of success on any trial, n is the number of trials, k is the number of successes, 1 minus p is probability of failure, and n choose r is a combination formula which is equal to n factorial divided by the product of n minus k factorial and k. So when we replace the combination formula in the first equation, it gives us a new equation of binomial formula. So now we are going to apply binomial formula in two cases. The first one will be determining the probability that at least one patient undergoing the new breast cancer therapy will not respond to the treatment. Um, our first step is to verify if we have a binomial setting, and our experiment satisfies this condition because it has a fixed number of trials, and which implies that our n is equal to 10 because this experiment has to be repeated on 10 patients. The second condition is also satisfied because we can define success as responding to the treatment and failure is not responding to the treatment. The third condition is also satisfied because the probability of success p is the same for every trial and it is equal to zero point 0.1. Lastly, recovery of one patient does not affect recovery of another. So our fourth condition that says that trials must be independent is also satisfied. So the next step will be now deducing the value of n, p, and k. We were told that this new therapy for breast cancer was tested on 10 patients from Western province. So our n will be equal to 10. We also know that the probability of success, P, is equal to zero point 0.1. However, we are not interested in the probability of recovering, rather, the probability of not responding to the treatment. Since we know that probabilities add up to 1, we can calculate our new value of p by subtracting zero point 0.1 from 1, and it gave us a new value of p which is equal to zero point 0.9. For the care part, the idea that at least one cancer patient undergoing this treatment will not respond to the treatment highlights that we can have one or more people who will not respond to the treatment. So we will be adding 10 cases and it is going to be very tiresome. To make this easier for ourselves, we can simply subtract the probability of having only 0 people who will not respond to the treatment from 1. This way, we will be accounting for the probability of having at least one patient who having at least one patient who will not respond to the treatment, which gave us a value of k that is equal to 0. Third step now is calculating the probability. We let X be having at least one patient who will not respond to the treatment, and Y be that no one will respond to treatment. We then substituted the values we got in the previous step into the binomial distribution formula, which gave us a value of py that is equal to 0.17374, which we approximated to 0.11. We then subtracted 0.11 from 1, which gave us 0.89 as the probability that at least one patient who will not respond to treatment. For the second experiment, we are to determine the number of breast cancer patients who must be exposed to the new cancer therapy before the probability that at least one person undergoing this treatment will recover completely is at least 0.95. As we did before, the first step is always to verify if you have a binomial setting. And now that the second experiment is a continuation of the first one, we can confirm that even the second experiment satisfies the four conditions. We move to the next step, which will be deducing the value of probability of k, p, and k, where p probability of k is the probability that at least one patient will respond to treatment. And from the information we have, it says that that probability is at least equal to 0.95. And then from the efficacy of the treatment, we can get the value of p, which is probability of success, to be equal to 0.10. Then the value of k, we can refer to the same analysis we had in the previous question to conclude that our k will still be equal to 0. So now we will move to the third step, which is calculating the value of n. We use the values that we got from the previous step as well as the binomial formula to make n the subject of the equation. And when you do so, you get an inequality which says that n should be greater than or equal to 28.4332, which we approximated to 28. For the consolidation part, let's start with the conclusion, a general conclusion of this experiment. It can be seen that there's an 89% chance that at least one patient undergoing this new breast cancer therapy developed by UGHE class of 2025 will not respond to the treatment. Again, UGHE class of 2025 must test its cancer therapy on at least 25 people. Those are 25, at least 28 breast cancer patients before the probability that at least one of them will respond to treatment is at least 0.95. So we also made a couple of assumptions. One of them being that UGHE class of 2025 would test the breast cancer therapy on only 10 patients throughout the experiment. If our value of n were to decrease or increase to another value, it would make our previous assumptions not relevant to the new value of n. For the second assumption, we assumed that the 10% efficacy of this new breast cancer therapy would not change throughout the um, entire experiment. If our P was to change, it would also imply that our previous calculations are no longer relevant to the new case. And the last one is that we rounded the result to whole numbers because we assumed that decimal points would be meaningless or would hold no value when we're talking about humans, because you cannot have a half a human. So, possibility of failure is that as long as cancer treatment, as long as cancer treatment can continue for years and years, the number of patients undergoing the treatment will continue to grow to grow and grow, thus approaching to infinity. So, at that point where n number of trials will be equal to infinity, binomial distribution will no longer be of help because it is only limited to experiments that have finite number of trials. Lastly, I'll talk about potential extension, which can be creating an open source software to compute this kind of prediction. This software can have features such as a simple documentation of what binomial distribution is and how it works. It can also have a calculator to calculate the probability by receiving n, k, and p. Again, it can have a calculator for the number of trials by receiving probability of k, p, and k itself. It can also have a button ask for help whenever needed. This brings me to the end of my presentation. Thank you.